Yo, what's up, guys? Welcome back. Episode 102 today. Yeah. So, let's take a look. So, I was gonna say something. I totally forgot. So it's alright. Let's take a look at Pokemon 102 today. We've got an execute. This is a good one. Execute. Let's take a look at the sound. I like the evolution of the execute.
Execute.
I can't remember what it is though, the evolution.
Execute. 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 Execute.
Alright, I couldn't hear any of that. I'm gonna have to restart.
Execute. 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 Execute.
Executor. I was gonna say that, but execute. Execute. Execute.
Execute.
Execute.
Execute. Execute. Execute. Executor.
Execute. 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 Let's do it one more time.
Execute. Execute. Execute.
Oh. Execute. That's our sound of the day. Yeah, let's take a look at a motivational quote today to get us started. Looks like we got here. Nothing in the world can take the place of persistence. Talent will not. Nothing is more common than unsuccessful men with talent. That's a long quote. Genius will not. Unrewarded genius is almost not. Too long of a quote. Let's do this one. There are 3 ways to ultimate success. The first is to be the kind. The second way is to be kind. The third way is to be kind. There you go. Be kind. Be kind. I like that quote. There are 3 ways to ultimate success. The first is to be kind. The second way is to be kind. The third way is to be kind. Mr. Rogers. Let's see who this guy is. American television host and author. Interesting. Okay. Let's take a look at our problem of the day. And we can get into some problems. Count the largest group. Well, I guess we might as well do it because it isn't easy, so. Given it is ran, each number from 1 to n is grouped according to the sum of its digits. Return the number of groups that have the largest size. There are 4 groups with the largest size. There are 9 groups in total. To be honest, I do not understand what this means. Like, you're given an integer n. Each number from 1 to n is grouped according to the sum of its digits. I don't understand it at all. We need to group numbers from 1 to n based on their digit sums. Lastly, we need to return the number of groups of digit sums with the largest size. I still don't really understand. We need to group numbers based on their digit sums. Digit sum. What is a digit sum, bro? I don't even understand what that is. Horrible task. Easy task. I'm 12 and work 3 full-time jobs and I cut on the weekend. I could do it. I have to kind of look up this question because I don't understand what we have to do. Count largest group. Group all numbers from 1 to n based on the sum of their digits. The sum of their digits. Eleven 10 is 1. 1 plus 0. 2. 1 plus 1. 3. 1 plus 2. 4. 1 plus 3. I grouped them. Okay, I think I understand, but I'm still not really 100% sure. So for I in, let's do range 1 to n. Okay, we know we need to loop from 1 to n. It says here, 1 to n. So we need to take a look at the length, right? So I guess if the length of I is equal to 1, then we know each digit sums the number. Maybe we don't need to calculate the length. Maybe we actually need to calculate the maybe change this to num. Maybe we can do like list comprehension here, so it's like for shit. How do you do list comprehension in Python again? List comprehension Python. And is equal to expression for item. So num for num in string num, right? Because we're looping through the string. How do we add each number though? Num for num in string num. We were close. Digit 4-digit in string num. But I think we need to wrap this in a sum too. Three times 12. Maybe we go to n+1. Get to 4, right? So then we go, okay, well, let's call this digit sum. So then we need some sort of like so now we loop through and we calculate, okay. So we calculated digit sum. Now what we want to do is we want to add that. So we go, okay, well, res is equal to digit sum. I'm trying to think here how we can do this. What is the pattern here, dude? I'm trying to think here. Digit sum. Go to to 10 to the power of 4. So I don't know what to do from here, bro. Group by digit sum. Keep track of how many numbers fall into each digit sum. Use a dictionary of similar structure where the key is the digit, not sum, and the value is a count. Find the largest group size. Okay. So we make a dictionary. Let's go dictionary. Right. We loop. Okay, we add the digit sum to our dictionary. Okay, so if my dictionary, we can do my dictionary digit sum plus equal to 1, else let's start with not, make it equal to 1, minus go dic digit sum plus equal to 1. Right, we get out of it, we go through all the groups, so we go, well, for my underscore dictionary, make some sort of count variable, and we count all the value in my dictionary dot values, right? Count values and return how many of the biggest values there are, right? So we loop through these values and we go, okay, well, let's do count values and return max, right? So we would need some sort of counting variable. So we would go, okay, well, our count is our max, sorry. Max val. If value is greater than max val, then we make max val equal to value. And then we need to count too, right? So we do count equal to 0. If we find a new one, we make our count equal to 1. But out here, we would make count equal to 0, but we increment our count plus equal to 1. We'll return our count. Three expected 4, our output is 9. Why the fuck did we get 9? Can we print our max val? How are we getting 9 then, dude? Let's print the dictionary, bro. Have a look at the dictionary. What is the dictionary holding? 1, 2, 2, 2, 2. Okay, we get 2 for 4, which is right. Oh, okay, I understand. We're not counting it properly, so... Okay, we need to... Okay, well... If value is equal to max val, then we can count, right? If the value is equal to max val, we increment the count. If it's not, we make value greater than max val. We can get rid of this. Make our count 1. Every time the value is equal to that, we increment our count. There we go. Hopefully that submits. There we go. Bit of a slower solution, but it did work. Interesting. Okay. Alright, I'll be back in a second. I am gonna go to the bathroom and we will be back. Okay, we're back. System design crash course, dude. Jeez, man. And then I gave my heart to a party girl. Alright, let's take a look at some of these problems again here. Let's take a look at surrounded regions. I believe we haven't done this problem. This was another one we could have done. 42% acceptance rate. Jeez, bro. Given no times on a matrix board containing letters X and 0 capturing regions that are surrounded. Connect. A cell is connected to adjacent cells horizontally and vertically. Region. To form a region, connect every O0 cell. Surround. The region is surrounded with X cells. If you can connect the region with X cells and none of the region cells are on the edge of the board. Okay. Okay, they connect adjacent to the region. To form a region, connect every O cell. The region is surrounded with X cells. If you can connect the region with X cells, and none of the region cells are on the edge of the board. So what I'm getting here from this question is that if a 0 is inside of the X, then we make it an X. Or if it's surrounded by X's. Right? pretty strict on time limit. The author is a horrible person. Okay, so I'm thinking my intuition here is, okay, we okay, so we loop through O, right? Okay. This is my intuition here, okay? This is how I think we should solve this problem, okay? We queue every single O, right? As long as it's not in visited, right? We haven't visited it yet before, okay? And we keep running BFS from each O, right? And when we're at that specific O, we check that if it's in the boundary, right? Because if it's in the boundary, then we instantly know that we can't surround the region, right? But if we go through every single O and it's not connected to a boundary, right? Then we know that this region can be surrounded. Hang on. Yeah, so that's kind of what I'm thinking here, but the thing is, we got to be able to somehow, like, my only issue is here is that we have to probably keep track of the path, right? The ones that we've actually, the O's that we've looked at, right? Because we would need to keep track of the coordinates of these O's. Because we could run BFS and keep running BFS, and then we get here, and then we realize, oh, okay, well, we can't go anywhere, right? Like, we're surrounded by X's. So it would end, right? And if our flag hasn't set us that we have found a edge, right? We're not on an edge, then we can turn all of these into X's, right? I'm thinking we maybe keep track of our coordinates in like an array or something, right? Of our current path, right? Of O's that we check. Because if our flag doesn't see that we've actually reached this part, then then we can just turn everything to an X. So that's what I'm going to do, right? So, get rid of all this bullshit. Okay, let's do rows is equal to the length of rows. Cols is equal to the length of cols. We want to print our rows. we want to print our calls. Okay. Sorry, the length of board. There we go, board 0. Where's the site visit set? Right, to keep track of all the cells we visited, we need a path. We'd probably want to initialize that inside of our BFS function, right? So we got our visited. We got okay. We need a directions array, right, to move. So let's make this up, down, left, right. So if we want to go up, our y would have to decrease, right? So 0, -1. If we want to go down, so go 0, 1. If we want to go left, we'd have to decrease here. And if we want to go right, we'd have to increase by 1. Alright, I think that should be good. Alright, and then what we want to do here is we want to loop. Okay, so for row in rows, for row in range rows, and then for call in range calls, we want to check, well, is this equal to O, right? So if board row call is equal to O, equal to O, and row call not in visited, right? Then we can call our BFS function. We can pass in our row, our call, our visited, and some new path, right? And some new path, right? We would do our BFS function. I think we really need to pass in all that, but I'm going to do it anyway. Def BFS, we pass in our row, our call, our visited array, our directions, and our path, right? We'd start by probably importing our queue here. So while queue, sorry, not while queue, from collections, import DQ, right? We come down here and we can import it. So now what we want to do here is we want to do, well, yes, we have to initialize our queue. Q is equal to DQ. All right, we want to queue.append row call we need to add to our visited, right? Okay, now we can do our while loop here. So while queue, then we want to pop, right? So we do, okay, well, row call is equal to queue.pop left, right? Now what we want to do, we want to go, well, for CR or nr nc in directions. We want to create our new row is equal to nr plus row. And our new col is equal to nc plus col, right? Then we want to loop, okay? We want to do, okay, well, let's check its inbounds first. So if 0 is less than or equal to new row, but is less than rows, and 0 is less than or equal to new col, but is less than cols, and visited, okay, and new row, new col, not in visited, and the, is it board? Okay, and board, new row, new col, not in, new col is equal to O, right? So if it's inbounds, it's not in visited, and it's in, and it's equal to O, then we know that it's good, right? So let's do, okay, let's do edge cell is equal to false, right? Okay. So, okay, well, okay. Now we need to check, well, check if it's an edge. It's an edge, right? If new row is equal to 0, or new row is equal to rows minus 1, or new col is equal to 0, or new col is equal to cols minus 1, right? Then we can flip this to being an edge cell, right? Edge cell is equal to true, right? We check if it's an edge cell, okay? We check if it's in bounds, it is in bounds, and we check if it's an edge cell, right? Because if it's an edge cell, we don't do anything with it, okay? If it's right. So I think here, what we can do here is, well, we come out here outside this while, and I guess if edge cell is equal to true, then either way, we want to add to current path to go back to, right? So we would do, okay, well, path dot append new row, new col, right? And then obviously we'd have to q dot append new row, new col, right? And obviously we'd have to add it to our visited set, right? Because we have visited it, so visited dot add new row, new col. Okay. Visited and Q. Alright, if it is an edge cell, so if edge cell is equal to false, right, so it's not an edge cell, then we can simply go through this. We can go, okay, well, for let's do old row, old call, in path, right, we can make, okay, well, board, old row, old call is equal to X. We'd make them all X's, right? I believe that should work. Down, left, right. Got a simple function here, simple flag that tells us, right? The flag's false. Then we would just make everything X. If it's true, right? If it is an edge, then we just keep it, right? Let's see what happens. It's never closed. Okay. I don't know if this will run properly, but or if this will pass. Ideally, but I think I'm thinking about this right, you know? Like, I really believe I'm thinking about this problem right, hopefully. Oh, it's equal to X. We need to make it equal to X. Why the fuck is it not changing this one? Why we're not adding it here? Path.add row call. Okay, he's in our heart. Did I get my heart to... So it changed to an X, but it should be a 0. We shouldn't be able to get to this part, right? It should go through, okay, it should see the 0 that it's not in visited. It'll come in here, it'll add it to visited. It'll see here that it's 0. Then if the new row is equal to 0, or new row is equal to rows minus 1, or new call... Let's see if it gets here. Getting here. Then I give my heart to a party girl. Okay, it's not getting here. Maybe I've got something wrong here. I'm checking if it's an edge. Well, if it's an edge, it would be 0. This would be 0. This would be 0. The length of row is -1. I think I've got it right. What is wrong here? Why is it not getting here? Let's take a look. It's gonna be something stupid, bro. I guarantee you it. $130. If row call, the node you call BFS on, is already on the edge, that also counts as an edge connected region, but you're only checking the neighbors inside the loop. How did I not see that, bro? So what we need to do here, we're only checking the neighbors here, right? So we need a pop, and we need to check here. Okay, so if we need to get this condition over here too. I guess we can check it out here, because technically we're not going to. Shit. God, man, I need to go to the bathroom again, bro. What is going on right now? We need to check row, coal. Okay, is there going to be a TLE there? Oh, it submits. Damn. Okay. We solved it. Damn. What is this guy doing? Is this a... Okay. Just checking the bounds here. Pretty proud of that. I'm pretty happy about that solution. You know, that intuition was definitely there, so I'm happy. I'm definitely happy that we solved that, you know. Yeah, that was definitely, I'm very happy about solving that. I mean, we had that one bug there, you know, didn't realize that we were only checking the neighbors there, but you know, that was definitely a good solution, a good solid BFS solution. You know, the intuition was there and everything, so I'm happy about that. Let's feels good to solve this. Feels good to solve this. I'm gonna post my solution here. BFS solution. Favorite roll call is a O of n times n. O of m times n. We need the rocket emoji, bro. Let's get the rocket emoji, dude. The rocket emoji always gets people clicking, dude. Man, I have to go to the bathroom again, bro. Like, this is insane. Like, okay. I'm gonna quickly go to the bathroom and I'll be back again. Okay, we're back. To go to the bathroom again, man. Jeez. So we did do this one. Let's take a look at number of connected components in an undirected graph. I think we have looked at this one. Number of connected components in an undirected graph. For graph valid tree. Leetcode. Oh my gosh, dude. No way. Redundant connection. I know this one. We did look at this one a few days ago, and I remember struggling with it. We're going to take a look at it again. Maybe we can kind of see it better this time. This problem is trees an undirected graph that is connected and has no cycles. You're given a graph that started a tree with n nodes and labeled from 1 to n with an additional edge added. The added edge has two different vertices chosen from 1 to n and was not an edge that already existed. The graph is represented as an array of edges of length n, where edges I is equal to a1, b1 indicates that there is an edge between a1 and b1 in the graph. Return an edge that can be removed so the resulting graph is a tree of n nodes. If there are multiple answers, return the answer that occurs last in the input. A1 and B1 in the graph. Return an edge that can be removed so that the resulting graph is tree event nodes. There are multiple answers. Return the answer that occurs last in the input. Those you can find. Trying to think here. Can we run DFS on this, bro? Like, but how do we know that this is the edge that we have to remove? Like, how do we find out? Skip. Okay, so we started. I guess we can start with DFS from this node. We can get to all the edges. Trying to think here. What was an array of edges of length n where edges I, A1, B1 indicates that there's an edge between nodes A1 and B1 in the graph. Trying to think what the best way to solve this is, right? Like, I just... Okay, let's start by creating our JSON list, right? So def JSON list, we pass in our, I guess our edges, right? Create a graph in here, right? For edge in edges, right? We can do, okay, well, edge, sorry, AB is equal to edge. Graph A dot append B, graph E dot append A. For I in so okay, if A not in graph A is equal to this, B not in graph B is equal to the empty string, then we would append, right? And we would just return our graph, right? Create our JSON list, so adj list So graph is equal to AGJ list graph. And let's print out graph. Right? Sorry, there should be edges. 213, 312. Okay, that looks right. Bro, this constraint is just so unnecessary. Like, yeah, you know, I don't really know. 684 redundant connection. Let's take a look at Leetcode.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem, redundant connection. We've actually already made a video for this one before, but I think I could make it a little bit better. The idea here is that we're given an undirected graph, so
Especially with
every single edge, for example this one, is always going to go in both directions. And they tell us that actually the graph that we're given does not have any cycles, but we introduce one additional edge, and this edge is not a duplicate. It did not already exist. And also, it's not like going to be a self loop. They tell us that by saying that it has two different vertices attached to it. And then they specifically tell us that we want to return the edge that can now be removed from the new graph such that the resulting...
if we go 1, right? Then we go to 2. From 2, we go to 1. Then we know that that's an edge. We know. Let's try it. Let's do, okay, well, For graph. Length edges, right? We can simply length edges might need DFS on our node. I visited so we need to make some sort of visited array. Is equal to set. Maybe we need to return that edge too. DFS. So def DFS plus in our node, our visited, and our edge to return, right? Guess our edge to return would be some sort of array, right? We can loop through, right? And we would go, okay, well, shit, man. Well, if node and visited, then we instantly dot add node for graph node in visited. Sorry, for graph. Sorry, for neighbor in graph nodes. We loop through our neighbors, right? Jeez. Trying to think here, bro. For neighbor and graph node, if neighbor. A neighbor and graph node. Okay, well. And we'd have to go, okay, well, DFS, neighbor visited our edge, right? Code auto-append. Code auto-append. Let's do node neighbor. Add the edge, right? So maybe we'd have to do a new visited set every time. See, I don't know, bro. I'm kind of all over the place. Like, visited.add node. Look through. See it, code or append that node. Visited. Let's print. Let's have some sort of like res array here. And like print our res. Car is not defined. Okay, let's do like, let's turn this into a set. Right, so let's do like res is equal to set. Right? We can res.add. Okay, if node neighbor in not in set or sorry, not in res or node or neighbor node not in res, right? So yeah, I don't know, bro. I have no idea. Let's just watch the video, dude. At least we got the
graph
cycles.
is now going to be a tree. So just to quickly summarize, they originally said that they gave us a tree, then they added one more edge, and now the graph is no longer a tree, but after we can identify the edge that can be removed, then we can end up with a tree once again. And it might be possible that there are actually multiple edges that could be removed. And so if that's the case, they tell us that among all of the edges, we would return the last one. So this problem has a lot to do with graph theory. That's why I think this is actually a fantastic problem, because they intentionally word the problem in such a way that you need to know certain things about graph theory. And I'll try to cover those as best I can in this video.
I think I did watch this
but also,
video
if you
as
just
well.
want to learn
Sad
more
thing
about
about
these things in general, you might be interested in the DSA for beginners or the advanced algorithms courses. So the main facts about a tree are that it is generally connected and it does not have cycles. So what they're telling us is that they originally gave us a graph that was connected and did not have cycles. Then they introduced one additional edge. In this example, I guess that edge was this one, 2, 3, and now the graph is no longer a tree. And it makes sense. If you got rid of this edge, we would have a tree. You could draw it this way. I guess it would probably make more sense. You put like the 3 over here and the 2 over here. Now it probably looks like a tree to you. But keep in mind that for a graph like this one over here, I guess the edge that we are removing is this one, 1, 4, and this might not look like a tree, but if you were to rotate it and redraw it, it might look something like this, where you have a 2 connected to the 3 and the 1, the 3 is connected to the 4, and 1 is connected to 5. So when you draw it this way, it kind of looks more like a tree. It doesn't necessarily have to be a binary tree. We could have a graph that looks like this. That's also considered a tree. So just keep that in mind. So now it's easier to interpret the problem. When they tell us that we want to remove an edge from the graph to make it into a tree, now we kind of know what we're looking for. We want to remove an edge so that we eliminate any cycle that is in the graph, because we do not want to have cycles. So knowing that, when you look at this first example, it's actually possible to remove this edge and then we end up with a tree. And we could also remove this edge and then we also end up with a tree. We could also remove this edge and we also end up with a tree. So why is the solution 2, 3? Well, that just happens to be the last edge in this list. When we look at this problem, we can identify the cycle pretty easily just by looking at the graph. We see that this is the cycle here. So probably we could remove this edge or this edge or this edge or this edge to eliminate the cycle. We can't really eliminate this one because it's not really a part of the cycle, and then we would end up with a disconnected graph anyway, so that's not going to help us. So now among these 4 edges, which one should we eliminate? Probably the one that shows up last. So I guess these are the first 4 edges, these 4, and the last one is 1, 4. So that's the one we eliminate. These are the edges that are a part of the cycle. We eliminate the last one. That's what we return. So now this problem has become a cycle detection problem. We just have to detect.
I'm curious, did we detect all cycles? Okay, no, we didn't this one, so it's wrong. We detected 1, 5 as a cycle.
The cycle, or at the very least, identify all of the edges that belong to the cycle in the graph, and there's guaranteed to be a cycle, so don't even worry about that. There's guaranteed to be a cycle based on the problem description. So if you were to identify that these are the edges belonging to the cycle, then one thing you could probably do to solve the problem is just iterate over the input list in reverse order and just check, is this one a part of the cycle? Well, it's not. And then you could go to the next one. Is this one a part of the cycle? Well, yes, it is, because maybe we threw those edges into some kind of data structure like a hash set. That is a perfectly valid solution. And you can see the code for that solution directly on Leetcode.io if you are interested. It should be available in most languages, so probably your language of choice. But I want to take advantage of this problem because there's actually a more natural solution to this problem. It involves a relatively advanced data structure called the disjoint set, or I prefer to call it just union find, because union find can also be used to detect cycles. I'm not going to go super in depth into exactly what this data structure is. We will be implementing it in the coding part of this problem. If you do want to learn this data structure more in depth, you could consider checking out the Advanced Algorithms course on Leetcode.io. It has a video, practice problems, as well as this article and a bunch of animations and things to make it easier for you to learn, code snippets in most languages, but you definitely don't have to. So if this is interesting to you, you can consider it, but anyways. So union find in the context of this problem is what I'm going to be going over now. The general idea behind union find, I guess I will use this second example to illustrate it. We start out with a bunch of individual nodes. So in this problem, they tell us that we are given nodes numbered from 1 to n. You might be wondering, well, what exactly is n? They don't even tell us how many nodes that we're given. That's actually a part of graph theory. If we started out with a tree, that means we had some kind of connected graph without any cycles. If that's the case, I can tell you that if we had n nodes, we must have had exactly n minus 1 edges. Because you can see that if now I were to introduce one more edge into this graph, assuming we cannot have duplicates, it's definitely going to result in a cycle like this one. And that's always going to be the case. This is just a relatively simple fact of graph theory. And so thus, if by introducing one more edge into the graph, we added a cycle, we can guarantee that the number of edges is exactly equal to the number of nodes. So it's not a coincidence that in this example, we have 5 nodes and we also have exactly 5 edges, because we're guaranteed that there's only one cycle in the graph. And before we added a edge, there was not any cycle in the connected graph. If we were to add one more edge, that could cause problems, because then we might end up with multiple cycles, and that is not what we have to deal with in this problem. We do not have multiple cycles. So now that I've convinced you that we have exactly n edges and n nodes, now we know what n happens to be. In this problem, it's going to be 5, so we can start out with 5 individual nodes like this. This is kind of how the union find algorithm works. So I will draw the 5th one down here. So what union find will do is it will take 2 components and basically union them together by connecting them via an edge. So the way we can use that algorithm to help us solve the problem, I'll just briefly do a dry run right now. We are going to go edge by edge, and we are going to keep connecting the 2 nodes that the edge belongs to. So for 1, 2, we would connect 1 and 2 together. For 2, 3, we connect 2 and 3 together. For 3, 4, do the same thing, just connect them together. And now that we want to connect 1 and 4, sure, we can do that. We can introduce an edge just like this. But the great thing about union find is that it can actually be used to tell us that this edge that we have introduced, we have actually not connected two separate components. In other words, this can tell us that 1 and 4 already belonged to the exact same component even before we added this edge over here. We didn't need this edge. 1 and 4 were already connected. That's what union find can do for us. And so now you tell me, if that's what union find can do, how can we use it to solve this problem? Well, what that means to me is that 1 and 4 were already connected. There was already a path from 1 to 4, and now we introduced a brand new edge. And given that the edges are undirected, we have introduced a cycle. We have just finished the cycle. This is a cycle. So now you tell me. We already knew this was a cycle detection problem, but we wanted to return the last edge in the input that belonged to that cycle. So what should we do now? Well, by definition, if we just completed the cycle, the edge that we just visited was the last edge in the input that belonged to the cycle. So that's the edge that we can return. So as soon as union find tells us that we have connected two nodes that were already connected, that's the edge that we want to return. So this is how I'm going to be solving the problem. I'm going to briefly talk about how union find works, like as an algorithm. These are the nodes that we start out with. So what we do edge by edge is say, okay, 1 and 2, we want to connect them. So what we say is one node is going to be the parent of the other node. So in this example, we could say 2 has a parent of 1. All of the rest of these technically have a parent of themselves. So they kind of do that. And then we say, okay, 2, 3, let's connect 2 and 3. The way the algorithm works is we will go to 3 and find the parent of 3. Well, 3's parent is itself. We will go to 2. We will traverse up the tree to find the parent of it, the root parent, which in this example is 1. And then we will connect the smaller component to the bigger component. So in this example, rather than doing something like this, where we connect 1 to 3, this would be inefficient because look, it's kind of like a linked list. It's going to be long to traverse. We would rather have a graph that looks like this, where 3 is the child of 1. And now we will add 3 and 4, connect 3 and 4 together. So since 4 is smaller, I guess you could do something like this. You could have 4 as the child of 3, but remember how I said we want the root parent of each component. The root parent of 4 is itself, but the root parent of 3 actually is 1. And the reason we want to find the root parent is because then we can do something a bit more efficient and take 4 and connect it directly to 1. You can see how this tree is a bit more flat than the previous one. We want the height of this tree to be as small as possible. And this specifically is called path compression. And the other thing I was talking about is called union by rank. And these things are covered pretty in depth in the advanced algorithms course. And it's not like super trivial to cover this. And I also won't be covering the time complexity in depth, but I will tell you that given that we are doing path compression and union by rank, each of these operations is going to be relatively efficient. Going up the tree is going to be almost proportional to constant time. It's a mathematical function that I won't go into, but practically speaking, it is a constant time operation. But anyways, to now finish up this example, now we will be connecting 1 and 4. And so if you remember, for 4, we want to find the root component. It happens to be a 1, the root node, sorry. And then for 1, we want to find the root node. It happens to be 1, because for 1, it's going to be self-looping. And so now, that's how we detect the cycle. We find that 1 and 4 already belong to the same component. They have the same root. And thus, this edge will introduce the cycle. So this edge is the one that we want to return. So now I'm going to code it up to briefly discuss the time complexity. Since we are going to be going edge by edge in the input, and that's going to be proportional to the number of nodes, you could say that the time complexity is the number of vertices plus the number of edges, but these will be roughly equal. So I think you could just have one of these terms as well, and that would be fine. To be a bit more technically correct, you could say that you're multiplying these by the function I was talking about, but that one is practically constant, so it doesn't really matter. So let me clear this, and a couple...
A little bit of a confusing explanation.
Things that I didn't really talk about in the drawing explanation, just because these are just implementation details of union find, is that we maintain the parent of every single node like this. So we want to have an array that's like of size n, where n in this case, like I said, is going to be the number of edges, so like that. Now technically we want the index of this to be a node, so let's say the ith node will map to its parent. We know that the nodes that we have are actually numbered from 1 through n, so we really want to skip 0, and we can do that pretty easily. So I'm going to actually implement this with list comprehension, a feature of Python. If you want to learn more about that, you can check out my Python for Coding Interviews course if you're interested. But it's just like this. So for I in range n plus 1. So for every node I, initially its parent is going to be itself. So that's what I'm doing here. This should just create an array that looks something like this: 0, 1, 2, 3, 4, 5. I also want to maintain the rank or size of each connected component. Initially, we could just say it's going to be 1, so this one is a bit more simple. We can just initialize an array of size n plus 1, where all the values are 1. Now, there's two main functions to implement with union find: the find function and the union function. That one's a bit more complicated. It takes two nodes. I'll call them n1 and n2. And let's just assume that we had these two functions implemented. And let's say this function will return true if these were not already connected. Otherwise, in this function, we can know that they were already connected by getting the parent of each. That's what the find function is going to do. So I'm going to assume it just works. And then I'll do this: find the parent of n1 and find the parent of n2, the root parent. That'll give me p1 and p2. And if p1 is equal to p2, I'm actually just going to skip the union operation and just return false. I guess I could have completed the union operation as well, but in this problem, we don't really need to. So technically, this isn't a correct implementation of union find, but it works. In the context of this problem. So I have my return false and I have my return true. So assuming that these two are fully working, this is how I could finish the problem. I could go edge by edge and unpack the two nodes within each edge, and then I could do this: union them together. And if this returns false, if not the return value of this, then I'm going to return this edge. This was the edge that was redundant. So that's pretty much it. And now to actually implement these two functions, this one isn't too bad. We could do it iteratively, but doing it recursively is a bit nicer because we can do something like this. We can check if n is already equal to its own parent, then we can stop. Then we can just return itself. Or you could write it this way as well, parent of itself. Otherwise, we want to find the parent of itself. So we can pass in its parent and just keep going up the chain, like recursively. And then the return value of this should be the root parent. And so I want to set the parent of the current node to be that. So this path compression going up the chain, it will set every single node that we encounter, and it'll change the parent of each node to be the root node. And then from here, we can just return the same thing that we were returning up here. One little way to condense this piece of code is to see that this is duplicated down here. So we could actually change this to a not, and then within that function, or in that if statement, we could move the function call there. And if this doesn't execute, we'll end up returning the parent anyway. And if it does execute, then we'll return the parent. That's why I'm not changing this to be return n. I want it to be return parent of n. But that's just a minor change. You could leave it the other way.
Swerving off the drugs cause mayhem. Pow, pow. Da, 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 da. Okay, so we start off our code with parent. We have a hash map, right? Okay, so we start off. Okay, so I'm gonna go AB in edges. Okay, if U not in parent, let's actually make this graph because we usually do, right? If A not in graph, then graph A. So we're just generating the empty list, right? The hash map, sorry. Graph B is equal to this, right? If not union V, okay, so then we would run this part here. If not union A, B, return A, B. Okay. We're building our list, right? And if it goes through here, we go if not union A, B, right? So I guess here, now we're gonna do our def union plus an AB, right? Root A is equal to find A. Root B is equal to find B. Def find. Let's do like X or something. If parent, okay, if the graph of X does not equal X, and parent of X is equal to the find parent X. So we're going to call this function again. This holds parents technically, right? This needs to be changed to graph. We're learning about the union find data structure, baby. Graph. Graph, right? Get the union, right? So we find the parents, right? So this is finding the parents. When we find the parents, we go, okay, well, if the root of A is equal to the root of B, then cycle detected. graph root A is equal to root B, return true. And I gave my heart to a party girl. A hashable type list. Making a list here. We're not making a list. We're making it equal to A. This would be B. We start here, A, B, and edges, right? Okay, graph A is equal to 1, so we're making it the parent of itself. And then we're calling union, right? If it returns false, then we can know that this is the cycle in our function, right? We go 1, 2, right? We would call, okay, if not union A, B, right? So we would find A, find B, right? So if the graph of A does not equal A, so right now it would just return this, right? It would return 1 and 2, right? If root A is equal to root B, we don't have a cycle. Graph root A is equal to root B, return true. Okay, then we wouldn't return shit, right? We go to the next one. Okay, so we go, okay, 1, 3, right? Here we've already done 1, right? So B would just be equal to itself, right? Here in 5 minutes.
So let's begin by talking about what union find does. Imagine if you had some objects and you want to group them together according to some criteria. So one such grouping might be this. Now, once you have completed the grouping, you would want to know certain properties about the groups, such as how many groups there are, and if two objects belong to the same group. The union find data structure, as its name suggests, supports two operations. The first one is called union, which takes as input two elements, x and y, from the set of objects, and it joins or unions the groups containing x and y. For example, we can start with 0 and 2 belonging to the same group, and 1 and 3 belong to the same group, and when we call this function union 0, 1, it joins or unions the groups containing 0 and 1. So the final result will be all four objects belonging to the same group. The next operation is called find, and it takes a single object x as the input and returns the group that x belongs to. So now let's see how we can implement union find. We will first walk through the ideas and discuss the code at the end. Union find is useful in graph type problems. So our first step will be to cast the grouping in the form of a graph. And the way we do that is to connect all the objects that belong to the same group with an edge, like so. Now, remember we need to find a way to determine which group each element is in. To do so, we designate a representative element for each group. This element will represent the entire group it belongs to, in the sense that the find function will always return the representative. For example, when we call find of 4, the representative of the group that 4 belongs to is 0, so therefore we return 0. And of course, the representative will return itself. As another example, when we call find of 2, we return the representative of the group 2 belongs to, which is 5. Notice that 2 elements belong to the same group if and only if they have the same representative. So the representative provides a way of checking if 2 elements belong to the same group. So now we need to implement the other function, which allows the union of 2 groups. And to do that, let me rearrange this graph in a suggestive way. I've now put the representatives at the top and the rest of the elements of the group towards the bottom. Now, each group is represented as a tree, with the root being the representative. With this, we can introduce the notion of parents and children. For any given element, how do we find the representative? Well, we must travel upwards the tree towards the root. In other words, we need to keep traveling towards the parent until we reach the top. As an example, suppose we want find of 4. The parent of 4 is 3, so we travel upwards to 3, and the parent of 3 is 0, so we travel up to 0. And we would know when to stop if we just use the simple convention that the parent of a root is itself. So if we can keep track of the parent of every object, then we can very easily travel upwards the tree towards the root. So what about the union operation? Well, in this new interpretation, the representatives are the roots of the trees. So if we want to union 2 trees, we can just set the root of one tree to be the child of another. For example, suppose we want to union 1 and 2. 5 is the root of 2, which we can get by calling find of 2. And similarly, 0 is the root of 1. We then set the parent of 5 to be 0. And what this does is that it sets 5, which used to be a root, now as a child of 0. And all of the elements that used to be in the tree rooted at 5 now have a root of 0. And now these 2 trees have been unioned. Now we have the basic idea, let's discuss how we can implement this in code. We initialize this array called parent, where parent of I gives the parent of the object I. Initially, each element is their own individual group, so we initialize the array with parent of I equals I. Next, we implement this function find of x, which finds the root of the tree that contains x. So first, if the parent of x is not itself, then we know that we have not yet reached the root of the tree. So we travel upwards the tree by 1 step by calling the find function recursively on the parent of x. Otherwise, we know that we have reached the root of the tree, so therefore we just return x. And finally, we define the union function, which joins the trees containing x and y. So as we've seen before, we first need to find the root of y and the root of x, and we then set the parent of one to be the other. So that is the algorithm, and now let's discuss the complexity of this algorithm. If the data structure contains n elements, then on average, the height of the trees will be on the order of log of n. Since both the find and union operations involve traversing up the trees at most 2 times, the time complexity of both functions is O of log of n. The space complexity will be O of n owing to the parent array, which will have length n. Alright, I hope this video gave you a better understanding.
Definitely gonna do more union problems in the future. Union fine. I'm gonna take back a little bit to April 4th and have a look at what we implemented here. Just find cycles if neighbor. Another good way to do it, right? So pretty much what we're doing here is we're looping through our edges, right? Creating a visited set. Okay, that we would pass in, right? Because each time we're checking for the cycle, right? So that's why we have the visited set here. We're calling this DFS, right? Because if A's in the graph and B's in the graph, then we know that we've got a bunch of stuff in it. We've got all the edges in it, right? So we call this, okay? We go through here, we check if the current is equal to target, we return true. That's our base case, right? That's our cycle, right? We create the visited.add current for neighbor and graph.get current or empty string. If neighbor not in visited, then we add it to the DFS, right? And we call this and go back to we add our visited and we keep going, right? It's interesting. Definitely a good problem. Definitely a tough problem too. Definitely tough to think about. How do I like the problem, dude? I think they got rid of all the liking and stuff. You missed 12 days this month. Okay, I'm gonna call that for today. I appreciate you guys watching, and I will see you tomorrow.